All right, so today we're going to learn our final gas law, which is called Graham's law of effusion. So first, I just want to talk about what's diffusion versus what's effusion. Okay. You don't need to write these, but let's just talk. So diffusion is just when molecules move from high concentration to low concentration. Does anyone have like an oil diffuser? You know what I'm talking about? Or like, okay, what's the purpose of an oil diffuser? How many of you at home, you have like those plug-in scenty things? Okay, what's the purpose of that? The smell, right? To make your room smell good. So those particles, they diffuse from an area of high concentration, which is like where your scenty thing is, and they spread out about like your whole room. So they move from high to low. Okay, so diffusion, oh good, is when gas particles move from high to low concentration. All right, effusion, on the other hand, is just when gases escape from like tiny holes in a container. How many of you have gotten balloons from the party store so they're like filled with helium? Okay. Like not like the fancy, like shiny, like shaped balloons, but just like normal balloons but you fill them with helium. Okay. What happens after like a week? Okay, like they deflate, right? You lose gas. And so it's like there's just tiny pores. So when gases escape from tiny pores, that's what we call effusion. So today we're going to learn Graham's law. I've always been taught it's Graham's law of effusion, but sometimes you see it as Graham's law of diffusion. The purpose of Graham's law is just to calculate the rate of gases. So how fast do they diffuse or how fast do they effuse? So again, you still don't need to write much, only the bold. Can you see the bold? I'll underline when we get there. Okay. So the rate of effusion is just inversely proportional to the square root of its molar mass. So what that means, so what you need to know, gases with a lower molecular mass effuse faster. And this should be relatable. Do you remember way back the first day of this unit, you all did that PhET simulation? Do you remember like you played with that online PhET simulation? Okay, and we looked at those gas particles. The very first thing you did was you put 50 light particles in the box, and you put 50 heavy particles in the box. Which one moved faster? Do y'all remember? Light. Okay, so light particles move faster than heavier particles. Okay, so let's look at like, well, why? Why do light particles move faster? Okay. We look at this equation. Ke, what do you think Ke is? It's an energy. What kind of energy? Kinetic. So kinetic energy is equal to 1/2 mass times velocity squared. Okay. Kinetic energy is directly proportional to the temp in Kelvin. Okay. Right. So if you heat up a gas, they get more kinetic energy. If you cool it down, less kinetic energy. So then if two gases are at the same temperature, they have the same kinetic energy, which then makes mass and volume inversely proportional, which means if mass goes down, volume has to go up. Okay. So the big takeaway, and the only thing you need to write down is just lighter molecules move faster than heavier ones. All right, so then that brings us to Graham's law. Okay, so you do need to write down this equation. So Graham's law, we just say it's like rate A divided by rate B. It's equal to the square root of molar mass B over molar mass A. So when we do Graham's law problems, just make sure like they're diagonal. So whatever gas you decide as B, just one's in the denominator, molar mass is in the numerator. Okay, and then A, if rate A is in the numerator, molar mass A is in the denominator. Okay, so they're like diagonal from each other. And then it doesn't matter which gas you define as A or B. Okay, typically when I I just pick whichever one I'm going to solve for is probably in the numerator over the denominator. Okay, here's our first one. Okay, the rate of effusion of an unknown gas is 9.20 milliliters per minute. Under identical conditions, the rate of effusion of pure nitrogen gas is 14.65 milliliters per minute. We're going to identify the unknown gas using Graham's law. Okay, so when we do Graham's law problems, it doesn't matter which gas you make, A or B, before I set it up, I just think through like, where's my unknown going to be? And I'm going to pick like, do I want that in the numerator or the denominator? Okay. Typically, if you're going to solve for an unknown, do you like it in like the numerator, so above the line, or the denominator? Usually above, right, the numerator. So that's kind of my strategy of how do you define which one's A or B. Okay. So an unknown gas is 9.20 milliliters per minute. To figure out the identity, we're going to figure out the molar mass. So I want the molar mass to be in the numerator. That's like my personal preference. Okay. I prefer to solve in the numerator, not the denominator. Does that kind of make sense? Like that's how I'm going to decide where things go. So then the rate of that molar mass has to go diagonal. So then I know the 9.20 has to go on the bottom. Okay. Bless you. Okay. So then the rate of nitrogen is 14.65. Okay. And then I give you the formula for nitrogen. What's special about nitrogen?
It's diatomic.
Okay, it's diatomic. So what's the molar mass of nitrogen? Double that. What's 14.01 doubled? 28.02. Okay, if you happen to like flip these, we'll end up with the same answer. Okay, I just prefer to have x in the numerator. All right, so now we have to solve this. Okay, so first, let's just solve for the side. So what's 14.65 divided by 9.20? So type that in your calculator. Let's get an actual number. This one? It's nitrogen's molar mass.
Oh, okay.
Okay. You get 1.6. Okay. Equals the square root of x over 28.02. Okay. How can we get rid of the square root symbol? Okay. Let's square both sides. Okay. What's 1.6 squared? What do you get? Okay, so 2.56 equals x over 28.02. All right, so now what's our next step? Okay, multiply both sides by 28.02. All right, so what's 2.56 times 28.02? 71.7. Okay, so then the final step is to actually identify the unknown. 71.7, it's a molar mass. Okay, so then if you look at the periodic table, is there any element that has a molar mass of like 71.7? Right, like if you're looking, does anyone have a mass of 71.7-ish? No, right? Like we're not finding anything. Gallium is 69.7 and then germanium is 72.6, but nothing's like 71.7. Okay. However, there's some diatomics, right? Nitrogen is N2. So what element that's diatomic, if you double its mass is going to be about 71.7. Really close to that. So look at those diatomics. That's like the fluorine, chlorine, bromine, iodine. Which of those, when you double its mass?
Chlorine.
Good. Okay. If you double chlorine's mass, do you see how it gets really close? Okay. So then the way we know the unknown, it's going to be chlorine. Okay. Cl2 is really close to 71.7. Okay, here's our next practice problem. How much faster does hydrogen escape through a porous container than sulfur dioxide? Okay. So this one, instead of finding like an actual speed, it's just like how much faster? Is it 2 times faster, 3 times faster, 4 times faster? So the way we're going to do that, we're looking for hydrogen. We're just going to call its rate x, right? We're going to figure out how much faster it is. To make life easy, we'll just make the sulfur dioxide's rate like 1. Okay, so how many times faster than 1 is it? All right, so then now on the other side of the equation, you just have to make sure you line up the 1 and the x. Okay, so we're solving for hydrogen. Hydrogen is the unknown one, so that means hydrogen has to go on the bottom. Remember diatomics. So diatomics, we find them in gases a lot. So hydrogen is really H2. So what should the molar mass be for hydrogen? Okay, so 2.02 goes on the bottom. Okay. And then we're comparing it to sulfur dioxide. So that goes on the top. Find the molar mass of SO2, please. Okay. Bless you. Bless you. Okay, you with me so far? Okay, last class, I noticed a lot of people wanted to like square both sides to get rid of the square root. However, let's just solve for the right side. What is the square root of 64.07 divided by 2.02? Okay. What are you getting? Do you have one more digit?
Yeah, it's 5.6.
Okay. Okay, x over 1, is that the same thing as just x? Okay, so that means hydrogen just fuses 5.63 times faster than sulfur dioxide. And then with Graham's law, you can also just use a little bit of logic at the end to check your numbers, make sure it makes sense. Which molecules move faster, the lighter or the heavier?
Lighter.
The lighter. So which one's lighter over here? Okay, hydrogen. Does it make sense? Hydrogen's moving 5.63 times faster. Does that make sense? Good. Okay, if you calculated that sulfur dioxide is moving faster, would that be like a red flag that something went wrong with your math? Okay, last one. This time we have an unknown gas and it fuses 1.66 times more rapidly than carbon dioxide. What's the molar mass of the unknown gas? All right, so again, this one doesn't have like a specific velocity for a rate, but we know it's 1.66 times faster than CO2. You can use any two numbers out there as long as one is 1.66 times larger. So the easiest numbers to use are 1.66 and 1. Okay. Theoretically, can you use any numbers out there as long as one of them is 1.66 times larger than the other? Okay, yes. Should you just keep your life simple? Yes. Okay. So then again, you just have to figure out where like your molar masses go. Okay. So this time the unknown gas is the one that goes 1.66 times faster. So that means the unknown, it has to go like diagonal to the 1.66. And then the slower gas is carbon dioxide. So carbon dioxide has to go on the top. Okay. So what's the molar mass of carbon dioxide? Hold it, it's 44.01. Good. Okay, so now we have to solve for x. 1.66 over 1 is just 1.66. Do y'all agree?
Yeah.
Okay, so that equals to the square root of 44.01 over x. All right, what symbol do we want to get rid of? The square root. How do we get rid of the square root? Okay, so we're going to square both sides. So what's 1.66 squared?
7.5.
That's good enough. Okay, so 2.75 is equal to 44.01 over x. All right, how do we bring x up to the numerator? Okay, so multiply by both sides. Alright, so then we have x times 2.75 equals 44.01. Okay. How do we get x by itself? Okay, so divide by both sides by 2.75. Okay, what does x equal? What do you get?
1.1.02 or 03.
Try so you should be doing 44.01 divided by 2.75.
16 pretty much.
16 point
16 even.
even.
Well, it's got so it makes sense.
That's okay. Okay, and it's a molar mass, so what's your unit? Grams per mole?